As you can tell by the title, today's webinar is going to be exclusively on the Firetube boiler because of the significant number of these boilers that are out there in the marketplace and their popularity as the right boiler choice for just so many industries. And speaking of popularity, this subject that we'll be covering today has been brought about by popular demand, especially as it relates to the Firetube boiler, its design, its construction, and the essential engineering theorems which support this design. So this is what we're going to be covering today. I thought I'd give us just a little brief Firetube, a little bit brief history on the Firetube evolution. I think that's kind of important to start. Then we'll get into the major Firetube components, get into the construction of these horizontal Firetube boilers. Then I want to discuss the difference between the dry back Firetube and the wet back. There's a lot of confusion many times out there today relative to that question between the difference between the two. Then I'm going to get into the burner, two different types of burners that we'll discuss today, and then I'm going to get into the engineering, the theorems that I mentioned before, and then of course we always close with a summary of at least what I consider to be the real germane or important points. Now, as mentioned, I wanted to give you a very brief review of how the Firetube boiler evolved, and we'll start early in the mid-19th century with the steam locomotive. It's really a true example of the power of steam, which is the first law of thermodynamics. It was these behemoths of energy which played a major role in industrializing America as they moved freight and people from one end of the country to the other, from east to west. These babies weighed as much as 200,000 pounds. Yeah, that's 100 tons. These coal-fired or wood-fired beasts of burden, they could reach speeds of over 100 miles per hour while trailing fuel and water and freight and, of course, passenger cars. Now, looking at the business end of these steam locomotives, you find what is actually a Firetube boiler consisting of a furnace where the wood and coal was burned, a convection bank of water-submerged tubes through which the hot gases from the furnace transferred much of their heat to the surrounding water before exiting the stack in the front of the boiler or in front of that steam locomotive. Also note the steam dome at the top of the pressure vessel. That's where the steam was piped down to the cylinders for powering the wheels. And then we come to the early 20th century and the use of steam boilers to power gigantic ships such as the Titanic. This was one of the most luxurious passenger steamships ever made, and tragically, as you know, sunk during its maiden voyage on April 14th, 1912, losing over 1,500 passengers to the icy waters of the Atlantic. It weighed over 46,000 tons. That's about 93,000 pounds. It could carry about 3,300, 3,400 passengers. It was 60 feet from the water line to the upper, or I should say the lower boat deck, and it had a draft of 34 feet and a length of about 890 feet. It was powered with 29 Firetube boilers, as you see here. Now, 24 of those Firetubes were double-ended, so they had 6 furnaces each, 3 in the front, 3 in the back. And then 5 of the Firetube boilers had 3 furnaces, so they were single-ended. Now, this equated to 159 furnaces, which were fired with 825 tons of coal per day. Those firemen were quite busy. The 215-pound saturated steam from the boilers drove 2 4-cylinder engines that you see here and 1 low-pressure steam turbine for the electrical power. Its speed could reach 24 knots, or approximately 30 miles per hour, and it was going about 25 miles an hour when it hit the iceberg. So the Titanic's boilers were Firetube boilers, also referred to, as you know, as Scotch Marine. And as you can see, could be constructed to include multiple furnaces, such as the Titanic had, or a single furnace, as also shown in the picture on the screen in the center. However, in any case, you have a single shell housing furnace or furnaces, and then you have tubes, and they're all surrounded by water. And the hot gases then pass through them, and that's why they're called fire tubes. Now, what you are looking at are cylindrical fire tubes, but you also find another configuration, and that we refer to as the Firebox Boiler for low-pressure steam and hot water use. And they are very familiar, or very similar, I should say, to the locomotive boiler that we just looked at, and probably the Firebox evolved as a result of this locomotive design because it includes the large furnace for combusting various fuels, including wood and coal, and it has the convection tube section for grabbing the heat from the hot gases, which have already given up a large amount of heat in the furnace. And that heat we refer to as radiant heat, and we'll talk a little bit more about that later. So continuing on with a little bit of history on the Firetube boiler, and in the early to mid-20th century, boilers were not put together by a single manufacturer, but rather were assembled in the field. Now, this meant you had one supplier for the pressure vessel, you had one for the burner, one for the controls, and of course you also need a stack from yet another manufacturer to vent the products of combustion. Well, the problem was, who's responsible or whose responsibility is it when things go wrong? Well, the solution to this major dilemma came with the advent of the package boiler back in the late 1930s or early 40s, with a single manufacturer assembling and testing the complete unit, and then taking total responsibility for the entire package, and yes, in some cases, even the stack and breaching system. So the Firetube boiler design has been around, as you can see, for a long time, and as such has served in many industries for both comfort heating and process, where higher temperatures and pressures were required for heat treating or for just the motive force high-pressure steam provides. Now, on the screen now are just a random list of the typical industries where the Firetube boiler is applied, and believe me, it goes far beyond this list, as the applications are ubiquitous, to say the least. All right, that's enough of the background. Let's get into the construction of these Firetube boilers, and we're going to concentrate on the Scotch Marine or cylindrical type today, including those fire tubes with both the integral burner and the gun-style burner, each of which you see on the screen now. The construction starts with a flat piece of steel, which is cut to size to meet the length and width requirements for meeting the boiler's capacity in horsepower. The larger the horsepower, of course, the larger the sheet of steel. What is also done in this particular operation is the automatic cutting of the various openings in the boiler shell, such as the hand holes, the manways, and the outlet holes to accommodate things like the safety valve or valves, the feed water entry, the pressure controls, the vent, etc. So once this operation is completed, the sheet moves to the shell rolling area where the plate is formed into the proper diameter to meet the capacity requirement. For instance, in our particular case at Cleaver Brooks, the diameter of these shells ranges anywhere from 48 inches to 114 inches, depending again on the horsepower requirement. This just happens to be a smaller diameter in the picture, but at least you get the idea. Now, once the shell is fully rolled, it moves to the welding station where both the longitudinal and the circumferential welds are applied. These, by the way, are full penetration welds, and for the high pressure units, they also have to be x-rayed, and they have to be inspected by a third party who is an authorized inspector to assure weld integrity and fabrication quality. And this is only one of the several manufacturing stages the inspector will be witnessing and approving to, again, assure code compliance and product quality and safety. Now, at the same time, this particular operation is taking place, the tube sheets are being cut and drilled, and they will match the shell diameter, which is its internal dimension, or its ID, and you see that picture on the left. Completing the shell in tube sheet construction, the respective pieces come together, and the tube sheets, both the front and the back, are first tack welded into the shell before moving to the upender machine for fully welding the tube sheets into place. And as you can see, it is performed automatically and in the downhand position. Now, following the tube sheet welding, the pressure vessel moves to another area where all the flange connections, couplings, and stay braces for the high-pressure units are welded in place. Now, simultaneous with these operations, the furnace is being constructed, which includes rolling and welding of a flat steel plate again, and possibly also corrugating it, depending on the specific conditions. And I'll get into that a little bit, just a little bit later. Now, completing this operation, the furnace is then installed and welded into the pressure vessel, the install portion of which you see on the screen now on the right. Now, completing the furnace install, which also includes an inspected code welding procedure to the front and rear tube sheets, the finished pressure vessel goes to the stress-relieving oven for a specific period of time at 1100 degrees Fahrenheit. Now, this is to take place and is done to remove the stress from the weldments, preventing undue strain and possible cracking once the boiler is fired and brought online in the field. As all this is going on, and in another area of the plant, the boiler's sub-assemblies are being fabricated, and these include such things as the fuel train, the burner assemblies, pressure control manifolds, control panels, and the feedwater piping, all of which will come together with the pressure vessel during final assembly. Now, in yet another area of the plant, you may find the tube mill, which is forming and welding the tubes from rolled stock, and then automatically cutting the tubes to length to suit that particular Firetube boiler. Remember, the length of the tubes will change depending on the horsepower and the diameter of that boiler. The tubes are then taken to the boiler tubing area, where they are placed within the boiler shell using the drilled tube sheets to support both ends. And once the tubes are in place, they are secured to the tube sheets through three methods of attachment, and that's depending on the boiler's design pressure and the pass the hot gas is moving through. For instance, in the case of the high pressure and hot water boilers, the hot pass, or the second pass, those gases coming out of the furnace, is rolled and welded. The third pass is rolled and beaded. And the fourth pass, if there is one, is rolled and flared, because this is the coolest the gas will get before exiting. Now, the whole reason for this attaching procedure is to expand and seal the tube to the tube sheet, and at the same time, assure that we have a solid heat sink for the heat to pass through the tube sheet and into the water behind it once the vessel is filled with water. And that's what you see in those red highlights. That's the heat sink. We have to have good contact between the tube and the tube sheet. Now the pressure vessel is complete, and it's ready for the final step of its fabrication, and that's the hydrostatic check, which ensures all weldment integrity. Now, this is another third-party inspection stage, and as you can see, is applied at 1.5 times the design pressure of the boiler. In other words, with a 150-pound design pressure boiler, the hydrostatic test is at 225 pounds and held for a specific period of time. Any leaks, and the pressure vessel is taken out of production. The leak is repaired and inspected before again returning to the hydrostatic test for full compliance. Now the pressure vessel is completed. It's hydro-tested and moves to the final stages of fabrication, including the insulation and lagging, which is the casing. Those are installed. The burner throat and the liner refractories are installed. The front and rear doors are put in place. The burner and its components are affixed, and all the boiler's required trim is installed before moving to the test pit for firing, for a test fire, and a ring out of the controls before moving to the paint area, where the boilers receive several coats of enamel paint before they're being protected for shipping, be it crating or possibly wrapping in a heavy-duty protective plastic material. Okay, so that's basically how a horizontal Firetube boiler is constructed. Now let's look more closely at the design features and the engineering which goes into this design. And we're going to start with the dryback Firetube boiler. The dryback Firetube, as you see on the screen now, can be either a 2-pass, a 3-pass, or a 4-pass design. Now, what's on the screen now in the left-hand side is a 4-pass and includes a refractory-filled rear door which can be opened to expose the entire rear tube sheet and the tubes and furnace fixed therein. Remember, in a fire tube boiler, the flame and hot gases are contained within the tubes, and the water surrounds them, as is indicated in the cutaway. Now, with this dryback, you can also swing the front door to have full access to the front tube sheet as well. Now, all of this is necessary for inspection, for cleaning, and for tube and furnace repair if that's necessary. Now, refer, if you would, to the image on the right-hand corner while noting how the water surrounds the tubes and furnace. And this, by the way, is a depiction of a 4-pass fire tube boiler wherein the flame and hot gases make 4 distinct passes before exiting out the stack. We start with the furnace, which is the first pass, and understanding that the burner has been designed to match the volume and length of this furnace to allow the flame to only extend about, say, 2/3 of the way down the furnace itself while completing full combustion. Now, from here, all you have is hot gases traversing through the respective tubes, convectively and conductively transferring their heat before exiting. Then baffles, as indicated with the red arrows and that left-hand diagram of the cutaway, they are consisting of both refractory and steel baffles that form the divisions for channeling the flow between the various passes. The other horizontal fire tube is referred to as a wetback because of the water leg found between the turnaround plate and the rear tube sheet. Now, this eliminates the heavy refractory rear door found in the dryback and replaces it with a much smaller refractory-filled plug or access way, which is also seen in the picture on the screen. You'll also note that the wetback has 3 separate tube sheets, one in the front, one about 3/4 of the way down the pressure vessel, and one at the end. Now note the arrows pointing to each. We also see that the wetback has either a 2, 3, or 4-pass design. The large cross-section depicts a 3-pass, as denoted by the numbers indicating each gas passage, which is completed before exiting the outlet in the rear of the boiler in this 3-pass. The water leg, indicated on the screen, note that, which is formed between the second pass and the turnaround plate and the rear tube sheet, provides the heat insulation requirement for the rear of the boiler and is the reason for the wetback name. Now, as far as the advantages and disadvantages for each design, well, the dryback has the distinct advantage of providing easy accessibility to the rear tube sheet, revealing all passes, of which the second pass is the most critical in any fire tube boiler, be it wetback or dryback. With the wetback, as you can see, access to the second pass is very confined, and the space very difficult to work in when inspecting or repairing, especially on the smaller horsepowers. The main advantage of the wetback, of course, is the elimination of the heavy rear door refractory found on the dryback, which is sometimes cumbersome to open and reseal, and it's an ongoing inspection and possible maintenance issue. Now let's take a look at the capacities or size ranges for these horizontal fire tube boilers and their design pressure limitation. Now, as you can see, the size range is fairly large, between 100 and 2,500 horsepower, and that equates to about 3,500 pounds of steam per hour to a little over 86,000 pounds. In other words, these boilers now compete with the industrial water tube boilers at their lower end, the lower end of their range. Now, the design pressures go as high as 350 pounds, but normally you'll find these boilers in the 150 to 250 range, but they can go as high as 350 pounds. And by the way, I also wanted to point out that the wetback design will be used in sizes exceeding 800 to 900 horsepower because anything above that renders that refractory-filled rear door just too big and heavy to maneuver. Now, how about the burner? You will find both the integral burner as well as the gun type both of which are shown on the screen now. The integral burner, shown as a cutaway on the left, is a complete unit, including a pressurized wind box, blower fan assembly, and a burner assembly, all integrally packaged together and mounted on the front of the pressure vessel. The gun burner on the right uses a different concept with regard to delivering air. Rather than using a pressurized wind box and discharge fan, as is the case with the integral burner, the gun burner draws the room air in and delivers it to a blast tube before the air is straightened and then discharged across the fuel-air mixing device that we call the diffuser, or the baffle plate. Now, as far as firing modulation on these boilers is concerned, you'll find what you see on the screen now with the smaller sizes, say 100 to 150 boiler horsepower, offering high-low off firing in addition to full modulation. But when you get over 150 horsepower, they are all modulating burners for the most part, and the differences will be in the degree of turn-down capability. 4-to-1 turn-down is pretty standard, but you'll find a lot of 10-to-1 turn-down as well, especially in the larger sizes over 200 boiler horsepower, where the applications call for this kind of control to avoid excessive cycling because of large loads that may be varying. As far as fuel firing is concerned, the Firetube boiler is quite versatile. It's able to handle an array of fuels, including the standards, natural gas, propane, light and heavy oil, and then, of course, the biofuels, too. Now, this would include landfill and digester gas primarily, but also fats, waste oils, and greases coming off various processes. And as such, these are all renewable. So, we have a burner mounted on the boiler, and it's burning a fuel, whatever it might be. But what is the combustion control used to handle the firing? Well, you have a couple of choices. Either a single point positioning system that you see on the left with a single drive and shaft controlling the fuel-air mix with adjustable linkages and cams, or you have what is called the parallel positioning system with independent actuators controlling the fuel and air through a central controller. And that could include control of the FGR, the flue gas recirculation valve, if that option is elected, and is shown in the picture on the right. And you know, speaking of FGR, that of course is used to control thermal NOx emissions through the use of combustion gas mixed with room air in order to reduce the flame temperature without quenching it. The arrows on the screen will indicate where the FGR is introduced on the respective burner designs. And lastly, before moving on to the engineering portion of this program, I wanted to say something about the expected efficiencies for the properly designed Firetube boiler package. As you can see on the screen, and depending on boiler capacity, the fuel, the firing rate, and the operating pressure and temperature, these boilers are very efficient, averaging anywhere between 81 and 87% efficiency. However, there's a word of caution here. If FGR is required to reduce the NOx to, let's say, 15 parts per million or less, this will probably impact the turn down of the burner, which may increase the cycling. And that can cause some significant efficiency loss depending on the frequency of that cycling. So keep that in mind. Okay, so now we have the horizontal Firetube boiler constructed, and we've got it described. Let's turn our attention now to the basic engineering which goes into these boilers. First of all, we begin with the understanding that all boilers are built in accordance with the specific ASME standards, which, as you see on the screen now, the association was initially established by a group of engineers back in 1880. And that was because at that particular time, very, very serious occurrences were happening with boilers on a fairly routine basis. And here's some examples. Now here, unfortunately, these poor Civil War guys had survived the many rigors and horrors of war, only to be blown up by an improperly constructed or repaired boiler, the Sultana. And then there were many steam locomotives which blew up, killing and maiming many. And there were many other occurrences in various industries and touching many lives and many families. And this led to the creation of the very specific ASME pressure vessel codes covering both high and low pressure steam boilers. This code is very detailed in its instruction, and essentially it breaks down into two major sections, beginning with section 1, covering steam and hot water boilers, which for steam boilers operate above 15 pounds or 250 degrees. And for hot water boilers above 160 pounds, and that's hydrostatic head, and or above 250 degrees. These hot water boilers operating at these elevated pressures and temperatures would be considered high temperature hot water boilers, and would be built almost exactly like a high pressure steam boiler except for the differences in the connections. Now section 4 is the next category and covers those boilers operating below 15 pounds and 250 degrees, and those hot water boilers below 160 pound hydrostatic head and 250 degrees Fahrenheit. These are essentially heating boilers, though there are some low-pressure steamers that can be used for light process applications as well. Now, I mentioned a bit ago that ASME code is quite specific about how these boilers will be constructed. And as such, it will detail things like boiler plate thicknesses to be used, the type of welding to be applied, when stress relieving is necessary, including the temperature and time, when and what to X-ray, hydrostatic testing, and so on. So it's really quite specific, also requiring, and as previously mentioned, an independent inspector be in the plant at all times to witness specific boiler construction operations to assure the plant's quality procedures are not only properly followed, but they're applied. So with that as a sort of intro to the engineering portion of this program today, let me then begin by briefly discussing what goes into the sizing of the steam outlet connection for either a low or high pressure steam boiler. You know, the issue is maintaining proper velocity of the steam as it travels across the surface of the water inside the boiler and then leaves the nozzle and travels through the header valve. The issue is carryover, whereby boiler water is actually sucked up into the nozzle and into the steam system, causing wire drawing and seating problems with the header valve and possibly water hammer throughout the piping system. And this can be very dangerous, water hammer. So the design engineer calculates the required nozzle size considering the operating pressure and mass flow of the steam, and this is to deliver no more than 10 feet per second velocity across the surface of the water in the boiler, and an exit velocity not exceeding 5,000 feet per minute out the steam nozzle. So maintaining these velocities should keep the steam as dry as possible and avoiding the carryover problem I just mentioned. Now the next major engineering design area is determining and providing optimum heat transfer. And as you can see in a boiler, we have both radiant and convective forces working to transfer the heat from the burner to the water within the vessel. Focusing on the radiant heat transfer, it occurs in the furnace and is any surface which actually sees the flame. It's also the furnace, that is, the area for the greatest amount of heat transfer, mainly because of the significant temperature difference between the fire side and the water side. I mean, you're looking at over 2,000 degrees in the furnace and a substantially lower water side temperature. As a matter of fact, the furnace is at the power of 4 greater in temperature difference. So combining this significant difference with the mass flow and the turbulent velocity caused by the burner's combustion air fan, and if designed right, the furnace takes on a much larger role in converting heat energy to steam or hot water. And the reason for that is found in a principle of physics developed by Stefan Boltzmann and involving furnace emissivity, which is the ability of a black body, such as the furnace, to absorb heat energy with perfect efficiency at all electromagnetic wavelengths. Now, Stefan's constant defines the power per unit area emitted or absorbed by a black body as a function of its thermodynamic temperature. It's referred to as Stefan's law, the simple formula of which you see on the screen now. And it's the relationship between emitted power per unit area in watts per square meter, denoted with the M, and the thermodynamic temperature expressed with the Kelvin value and denoted with the T. And what this all means is the power per unit area is directly proportional to the fourth power of the thermodynamic temperature. And as such, the furnace becomes the real workhorse for the boiler overall, as it absorbs as much of the radiant energy as it possibly can in BTUs per cubic foot. And to maximize this radiant heat transfer, it's imperative that the burner and the furnace be matched precisely in order to assure the combustion is fully completed with very low to no CO formation and zero hydrocarbon. And the heat is delivered within its confines. It's very important that it be delivered within its confines to maximize the radiant heat absorption conductively. Now, with this degree of heat in the furnace, we often get the questions about which furnace type is most effective, and beyond that, the most durable, the plain furnace or the corrugated. You know, the fact is there is no difference between the plain and the corrugated furnace when it comes to efficiency, durability, and the life of the pressure vessel. This is strictly dependent on how the boiler is operated and how it's maintained. And then the construction relative to the weld attachment furnace to tube sheet is another criteria. The tube sheet to the shell, and then the ligament distances between the tubes mounted within the tube sheets themselves. Those are the differences that cause either the plain or the corrugated to fail. It's not the design of the plain or corrugated, it's how they're attached. Okay? However, the real reason for using corrugated versus a plain furnace is a combination of economics and design integrity. Economic, if the cost of the plain furnace, the material cost, is greater than the corrugated may be because of the design pressure of the boiler calling for a thicker or more expensive plate. Or on the other hand, the mean metal temperature causes the linear thermal limits to be exceeded, whereby the corrugated furnace may be chosen to reduce these limits because it uses a thinner plate. The next thing I wanted to cover from an engineering perspective is the convective heat transfer in the boiler, which is that amount of surface which does not feed the flame, but is only exposed to the hot combustion gases. Now it's the orange area shown on the screen now and representing the fire tubes. This is the area of design where the heat transfer engineer is looking very closely at the design which maximizes the Reynolds numbers, which is the ratio of inertia forces to viscous forces. And to a large extent, this dynamic is dependent on the velocity of the gas passing through the heat transfer surfaces. For instance, with velocity being the square root of its temperature, a value of less than 2,000 equals laminar or viscous, and a value of over 4,000 equals turbulent, and as such, a much better conductor of heat. The more turbulent, the better the conductive heat transfer across the metal surfaces. Because what we also want to do is we want to maximize the heat transfer coefficient, which is the proportionality between the heat flow per unit area and the delta T from fire side to water side. Now, it used to be for many years, and it's still the case in many specifications in the market today, that you had to have 5 square feet of heating surface in the boiler in order to maximize efficiency and protract or extend the life of the pressure vessel. And quite frankly, with many designs out there today, it still holds. But times are changing, and customers are asking for smaller footprints, less weight without sacrificing efficiency. They don't want to sacrifice durability and long life. So design engineers have been busy satisfying this need And the majority of the answer lies in the use of extended surface tubes in the convection area versus plain tubes, which you see on the left of the screen. Now, when looking at the convective heat transfer surfaces, the majority of fire tube boilers out there today use plain tubes, wherein the hot gases of combustion enter the tube, they turbulate for a short distance, and then they tend to plane out, losing some velocity, at the same time becoming laminar. Lower Reynolds numbers are caused as a result of that. So remember, the best heat transfer occurs when the hottest gas comes in turbulent contact with a water-backed metal surface. In this case, the laminar flow forms a cooler, ever-expanding gas boundary layer between the gas mass flow and the tube surface, reducing heat exchange because of its insulating nature. Now, to counter this, designers include sufficient fan horsepower to maintain a minimum velocity, overcoming the delta P throughout the vessel, adding additional tubes or gas passes to allow more BTUs to be absorbed, thus increasing the heating surface, the size, and the weight of the boiler. Now, in the optimized fire tube boiler design today, the plain tubes are replaced with highly engineered spiral tubes, wherein the number and spacing of the spirals and their angle to depth are closely analyzed. This is not only for the heat transfer purpose, but for pressure drop and tube life purposes as well. So, in the end, we are left with a totally optimized tube, which totally breaks up the laminar flow, greatly increases the heat transfer rate by up to 85% while delivering higher Reynolds numbers and heat transfer coefficients. This also reduces the number of tubes and passes, thereby reducing the fan motor horsepower, saving electrical energy, and the footprint, size, and weight of the boiler because of the reduction in size of the pressure vessel. This also meant the heating surface was reduced to about 3 square feet per boiler horsepower versus 5 square feet, but with no compromise to durability or the life of the pressure vessel because of the effectiveness of the heat exchanger, the boiler, to extract the heat on both the radiant and the convective side. You know, when I talk about fire tube boilers to various groups around the country and how they are changing, I often get questioned if boiler designers still go about the development as in the past with designs on paper and then prototype manufacture, then modifications to the prototype, or you scrap it and then start all over. Well, you know, when I started in this business back in 1964, that's exactly what was going on, and a lot of time and money was wasted. Today, however, things are dramatically different. Today, design engineers are using computational fluid dynamics and finite element analysis to not only design the boiler packages, including optimal radiant and convective heat transfer outcomes, but also the proper burner characteristics matched to the furnace to maximize efficiency and long asset life. Now, these designs are then affirmed through the use of complex algebraic formulas applied electronically using the finite element analysis tool I just mentioned, and affirming that maximum Reynolds numbers and heat transfer coefficients are indeed attained. The process also includes a thorough analysis of the structural implications when one is applying the amount of heat transferred in the boiler, along with the dramatic swings in delta T's involving varying circulation rates, I should say, and associated heat fluxes. For instance, analyzing the furnace and its stresses, because it's the area receiving the greatest amount of heat and the huge delta T's that I spoke about. What should the thickness of the furnace plate be? And should it be corrugated to lessen the cost or average mean temperature of the steel relative to its thermal expansion limits, yet providing sufficient strength in all the weld attachments? So, in the final analysis, when considering the fire tube boiler and its evolution, its construction, and its features, and the design engineering, I'm sure you'll agree there's a lot that goes into it. And I've really only scratched the surface during this brief time, especially as it relates to the engineering considerations. So with that, this is what I consider your takeaways today. The Firetube boiler is a versatile package suitable for a plethora of applications. I've only cited a few in this PowerPoint presentation this afternoon. Typical size ranges between 100 horsepower up to 2,500 horsepower as packages. Pressures up to 350 pounds. Construction, we follow the ASME code, all of us, very, very closely. Sections 1 and 4. 1 being high pressure, 4 being low pressure. There are both dry back and wet back horizontal fire tubes, with each having advantages and disadvantages. The fuel firing capability of these boilers is extensive and also includes the biofuels. The boiler is getting smaller in size and weight because that's what our customers want. But we have to do this as manufacturers and designers and manufacturers without compromising efficiency, durability, and the lifespan of that unit. Engineering is complex. It's getting more and more complex as the demands increase. But present-day advancements in computer technology has accelerated, and it's improved, and it's helped us tremendously. So with that,